Hello, everyone. My name is Piotr. I'm the co-founder and CEO of L2BEAT. And today's topic for all of you guys is exactly key derivation in StarkEx. And let me get to my first slide because, actually, the entire presentation is going to be just about this. I have other slides, of course, but the core of it is here in this picture. Basically, for those of you who don't know, StarkEx is a solution made by Starkware for building decentralized exchanges as ZK rollups or validiums on the Ethereum blockchain. So roughly the way it works is you've got a client, for example, like DYDX, they go to Starkware and they say, oh, we want to build an exchange, right? They get StarkEx, which is a set of smart contracts, a prover, and all of this nice other stuff. And then they get to deploy their own front end through which users interact with the exchange. So for example, for DYDX, they get to trade perpetuals. I'm not going to go into how perpetuals work. So when you log into DYDX, you're presented with this thing called, a pop-up in MetaMask that says to do something with the DYDX Stark key. And that's exactly what I'm going to talk about today. What is it? Why do we need it? How does it even work? And all of that. So how exactly does signing work on Ethereum? Well, at the very base level, if you want to sign a transaction, you prepare all of the data for this transaction. So you specify who this transaction goes to, what is the value of the transaction, what's the data associated with this transaction. You hash all of it, and then you do a digital signature. And digital signatures work in a way where, for example, for Ethereum, there is this thing called ECDSA, elliptic curve digital signatures. And we have a specific curve. I'm not sure if I'm pronouncing this right because I've only ever read it. It's SECP256K1, a beautiful name, total tongue twister. And this curve is what we are using for Ethereum for signing. We have a private key, which is a point on the curve. And then the signing works by basically taking this message hash, performing some operations, we get the signature. Now, all of this is good. Whenever someone else has the signature, they can verify that we have actually signed the message. Super easy, right? Well, because Starkware and StarkEx use the Stark cryptography, they unfortunately cannot use the same curve. So the SECP256K1 curve used by Ethereum, used by Bitcoin, is not unfortunately suitable for those exchanges. And the reason is I actually couldn't find any materials online, right? So why can't it be used? So I asked Starkware directly, and Lewis from Starkware told me that apparently the curve, this curve, I'm not going to pronounce it again, it doesn't really handle fast Fourier transform easily. And they need fast Fourier transform for polynomial multiplication and proofs in the Stark proving system. So they devised a different curve, a Stark curve, which is FTT friendly. FTT stands for fast Fourier transform, and therefore is Stark cryptography friendly, and therefore they only use the Stark curve and not the Ethereum curve. Now, this actually has some wide-ranging implications, right? Because if you have a different curve, you cannot actually reuse the same cryptography that you have on Ethereum, right? The logic, the underlying logic is the same. You take some points on the curve, you do some operations on them, you sign the message, it's fine. But unfortunately, because the curve has different parameters, the logic is slightly altered. And so, for example, if I were to take MetaMask, it has my private key on Ethereum, I want to sign a transaction, but this transaction is actually for a Stark exchange. Well, I cannot really do this because the curve is different. So the entire algorithm has different parameters, and unfortunately, I cannot sign it. So, well, how do we actually make this work, right? The first idea is well, maybe we can actually get wallets to support this Stark curve. There was a specification derived. They specified how the derivation for the Stark keys work, some specific information for hardware wallets to support it, for MetaMask to support it. But unfortunately, it turns out that it's really hard to convince people to support this, especially since uses of StarkEx at the time weren't really popular. The most popular StarkEx is DYDX by far, and StarkNet wasn't even a thing back then. So the wallet support is kind of out of the question. What can we do to allow users actually to be able to interact with this cryptography in like a easy way? So the next idea is, okay, wait. So the wallets that we use, either the hardware wallet that we use, or the in memory, sorry, not in memory, the hot wallet, the MetaMasks and other, they actually have keys inside of them, right? They have the keys for Ethereum. Maybe we can find a way to take those Ethereum keys and somehow derive other keys that we're gonna use for the Stark curve. And so they sat down for a minute and thought, okay, is there a process that we can use to take the keys that we have and figure out some new thing from them that actually no one else but the owner of the key can figure out? And here came the idea for what you actually see on the first slide, which is you can sign a message, right? You can sign a message, and if you never share this message signature with anyone, if you keep it to yourself, then this signature can actually become, or at least be the basis of, the private key on the Stark curve. So here's the basic idea. And this is code, and this is the exact code of how you do it, and I'm going to walk through it. First of all, you specify some message. The reason I left this out is because, if you can see here, the signature request actually specifies some data. And Ethereum has this specification for type data. You pass a JSON, it has some special fields. It's boring, not related at all to this cryptography thing that we're gonna do. So this is why message is just 3 dots. It can be actually anything, and it's specific to each application. Each StarkEx actually provides a different message to the user to sign. Now, so next thing we do is the provider request to sign the message. This line just pops up MetaMask, right? And the await means that the value is only returned when the user presses sign. So now we've got the signature, but actually the Ethereum signatures are 64 bytes long. I think that's the right number, but the key derivation algorithm expects 65 bytes for the signature. I have really no idea why they thought this was a good idea, but of course, each StarkEx now has to figure out what is the next byte to put there. And they put whatever they want there. So for example, for DYDX, for the last byte of this extended signature thing, they put 00 in the new version of DYDX and 03 for legacy signatures that use the different message and stuff. Okay, so now we have the signature, we have appended 1 byte, a completely arbitrary byte, but it has to be the same one if we want to reuse this. And now we hash it. So we get the hashed signature and convert it to a big int, offset it. I think it's right shift, but I'm not gonna make a bit shift by 5 in some direction. And then here is the fun part. Now we take the Stark curve with specific parameters and we say this private key is actually a point on this curve. Now you get to derive all of the other stuff like the public key and stuff. And so now we actually get everything that we need to sign messages. And this scheme actually has this nice property and here is an asterisk, I'm gonna come back to it. Nice property that if you, for example, want to do this operation again, you will get the same result, right? So let's say I log into DYDX on one browser, go in, sign in with my account. I sign a message with an Ethereum private key. This message gets hashed. This message gets put through the elliptic curve. I have everything, right? But then I either change my browser or clear the cookies or whatever. And now what happens? Now I no longer have this private key that was saved in my browser. I have to derive it again. And if I sign everything again, I get the same private key, which is great because it allows for key recovery, and actually the flow is super intuitive in that all you have to do is sign a message in MetaMask and everything seems fine. Now, here's the funny thing about this. You see this algorithm, right? It's actually not really documented properly anywhere. So there are libraries that StarkEx developed for getting this key out of the signature. There also is a documentation for StarkEx on how you can do this. But both those tools are actually for or most likely targeted at the exchanges themselves. So when I'm a customer of Starkware and I want to build my own exchange and I want to support all of this stuff, I actually can use those libraries, can use this documentation to put all of this into my system. So then when the users log in, they are presented with this prompt and they can log in. But what isn't documented is what actual parameters, what's the message, what's the appended byte, and actually there are some other nuances that I'm not going to get into. How is this different for any other system? So it's different for DYDX, it's different for Apex, it's different for Immutable X. So the way because at L2BEAT we've built a StarkEx Explorer that allows you to see all of the stuff that's happening on StarkEx, exit the exchange without interacting with their front end. And to do all of this, we actually needed to get the keys from the user. This wasn't documented, so we had to reverse engineer the front ends of each and every other system to get to see what the specific parameters are. What is the signature? What is the message that you get to sign? What's the special byte that you get to append? And part of this reverse engineering was done by actually going into the code that's shipped to the user in the browser and trying to unminify it and see what the parameters are. But that's really, really hard. So part of this reverse engineering was just overriding the functions that the code calls to talk with MetaMask, just inserting yourself in the middle and trying to scoop over the messages. So, oh, this is the signature that was just requested. This is the message, right? And this is what came back. And so now we get to actually use this information to try to derive the same keys that the exchange does. Now, this is all well and good, but unfortunately, there are some problems with this scheme. And I think the biggest one is the fact that signatures can be non-deterministic. And so this is actually a well-known property of ECDSA, elliptic curve digital signature algorithm, that you get to pick a random number whenever you sign. And if you pick the same number again, you can leak your private key. It's very bad. And so in the early days, the way all wallets worked is that you actually get a different signature every time you sign a message. Now, for newer wallets, it's actually been fixed. Let's say the signatures are deterministic. The random number is actually a hash of the message and the private key. So it's random, but also reused and also not leaked, and it's fine. But there are still some wallets that, for example, some old hardware wallets and other that actually do this kind of thing where every time you sign a message, you get a different signature. And so some users of the exchanges logged in, signed in, got their keys, the keys were saved, but they can never be recovered. If they ever lose access to the computer, if they ever lose access to the data stored in the browser, that's gone. They can never, ever access those keys again. And yeah, it happened for some people, which sucks. So this is one big problem of this scheme. Another big problem is the fact that the keys are actually stored in local storage, right? So if you get your computer compromised, your application compromised, someone manages an XXS, cross-site scripting, attack on, or maybe it's XSS, never mind, an attack on the exchange, right? They can actually get the private keys of the users, which is also really, really bad. We don't want this to happen. This is actually why MetaMask and other wallets are separate from the sites that you use, and the sites have to communicate through this weird mechanism of RPC and stuff. Because if it wasn't separate, if each site actually get to manage the user's wallet, well, the attacks for private keys would be constant, and people will be constantly losing their keys, right? So, so one last thing that I wanted to say about all of this is that the same thing, the same cryptography, which is that you need the Stark curve, so you need different signatures and you need different keys, and the same problems with this algorithm. So, like, if you just use the signature that you do from the Ethereum key, then you have non-deterministic signature problems. Then you have the phishing from local storage problems, is actually why the scheme isn't used for StarkNet. So for StarkNet, actually they got some wallets to actually support the Stark cryptography natively. And so the problems that I outlined here don't really apply. What applies is the fact that the curve is actually different and the cryptography is actually different. So you cannot use MetaMask for StarkNet. And that's what I'm going to leave you with. Thank you very much. And I'm giving it back to Marek.